recording and start screen sharing. Okay, that should be working. So, in the last lecture, we have started looking into the standard template library, and we were not quite finished with doing so. So let's go back to our STL demo project and let's continue. A short reminder first. STL offers a large amount of template-based classes, which started mostly as a collection of container types. Nowadays it's extended with quite a few more functions, but for our purposes we'll focus on the container types, as these are the most generically used. And we already have had a look at string, base string, vectors, lists, and maps, and then our time ran out, so we will continue with maps. Just a short reminder on maps. A map is basically a container type which allows to associate a value with a key, such that the values can then be retrieved or updated by key, which is very useful. Maps, the way they are made, are usually sorted, meaning that there is an order imposed onto them. So in principle, a cheap way to order something would be to just throw it as keys into a map and then retrieve it from the map in order, which may not necessarily always be the recommended way, but it's a quite neat workaround if one wants to be quick about it. And to demonstrate that, what we can do is we can create an own map key type. So let's first create a struct as my key, and this will need some constructor as some value, and we will add a body later and something to store the key as such. Let's say we want to store a unsigned char value 16. So in principle we are making here a key which basically is a 16 character byte array, and here, just for simplicity, we will only initialize the first one. Oops, the copy doesn't work. We'll initialize the first one with the value that we already have here. We will try to use it as a key in a map that will throw a compiler error, because we don't have yet defined an order for our elements, but we'll do that in a second. So as my key int map, and then we of course need some key as fun I. Okay, if we try to build that, it will complain. Wait, it's complaining about something else as well. Yeah. Okay, we use my map, so my map 2. We cannot reuse names. Okay, now we are at the right arrow. It is complaining that there is no less than operator defined for this type of value. So the map needs that in order to establish the order. One might think that one would also want to have like an is equals operator, but having just a less than operator already allows you to also make a is greater or is equals just by turning the operator around, or just by using it in both directions and then evaluating the result the right way. So for simplicity, the way this is implemented only requires you to provide one operator. And previously we have defined operators on our class, which is nice, but there might be cases where you want to have an operator for something where the object is already defined and you cannot change it. comma R. So it's nice that we can define operators for objects also outside the objects, which we'll be doing here, for example. And here, for simplicity, we will just make a loop which will compare the individual entries. Return false, of course, if nothing is found, and if L.value von I is less than R value von I, then return true. So we just check for the first situation where this condition is met, and then we say that the whole operator returns true, else it return false, meaning that either they are bigger or they are equal. And now when we try to run it, it will compile just fine. Of course, it doesn't do anything since we haven't done much more than just edit it. But this already, I think, demonstrates how this mechanism works, and we do not necessarily need to fill in much more other entries. Okay. The next thing that's quite useful about maps is that let's create again let's maybe use one of the maps. Let's create it again one map. Let's go with in principle it doesn't matter, we can just take instead of simple map list, let's list this one. Respectively we can also change this and use the integer first, which might be simpler. Oops. Okay, my map 4. Okay. Technically it's then 0. So let's capital 0 to put all of them are the same. Okay, now let's say we comment out a few of them. Yeah, those. Let's say. The map, as I think I showed you already earlier, has this find function, which can be used to retrieve one of the values. But there are use cases where one might be interested in retrieving one of the values without exactly knowing which value is there. So assuming you have some ranges with which you are working as keys, and then you want to find a value without going through the whole map, but you don't have the exact key. So what you can do is you can use the upper bound function. It returns you an iterator like the find function, but the way it works is that even if you look for a key which doesn't exist, like let's say the key 5, which here is commented out, so it's not entered into a list, you will get a result. And let's make a few tests. So let's look for a key that does not exist, and because there's a second function as well called lower bound. So 2, and then we repeat that. 3 and 4, and then we look for a key which exists, and we can then in principle have bound 5% d comma first. we are not interested. First is the key, as you might remember. Here we are not interested in the value. We just want to see how the map behaves with regard to the keys. And in principle, you should always check, of course, if this is not null, not 0. This is ungleich. Why is that complaining? L1 should not be complaining. This place, a space got in there. It should be there. Okay, so of course we needed to change here the value 4 3 2. Yeah, so now it's safe, and let's and we should of course make new lines. Okay, let's run it. Okay, and as you see, so we were looking here for 5. 5 doesn't exist. So what it does, both functions, it will give us the next key, which is when we use the upper bound or lower bound function. If the key doesn't exist in both cases, it will return us the next key after it, so one that is bigger, and it can be arbitrarily bigger. So if we would, let's say, remove 6, or for a better example, let's look for 4. It will still work the same way. It will give us both will give us 6. And the and when we are looking for a key which exists, then the difference between the upper bound and the lower bound function becomes apparent, as the upper bound function gives us always a key that is bigger than what we were looking for, while lower bound gives us greater or equal to what we were looking for, depending on whether the key exists in the map or not. And depending on your use case, one of those functions might be a better suiting candidate. Of course, if you want to implement something that gives you like the smaller or equals or so, this needs some additional work, because those functions are not present in the map. There are two ways how you can achieve such a goal. First of all, if it is easy to reverse the order of keys, so for example, instead of here putting numbers, you would just put negative numbers, or if you can change the sorting operator, then you could achieve this. The other option, a more manual one, would be of course to get what using, for example, the lower bound a value, and then using, since you have an iterator, you can go with minus minus to the previous one. Usually this works just fine, and then if you have the previous iterator, then you can check the keyword that fits your additional criterion, and so on. So the important thing is to be able to find something close to your result, and then you can walk from there quite efficiently through the map to add additional criterions if you would have any for your search approach. Another thing that can be done with those maps, when we look on the definition, is that it actually takes the template takes actually quite a few more arguments than what we use. We only used key and type, but we have also a less from key, which will be a pointer for something that so basically here we could provide an own comparison operator, which will be only valid for this map, or rather a comparison function, to be technically correct. It will not be an operator, just a function. And the idea here is that then you could really impose any order, and you could, for example, have two maps which have both the same object as a key, but they impose completely different orders just based on this less than function which you pass to it. And the additional thing you can pass is the allocator, which will be responsible for memory allocation. So if you want to allocate memory using some own mechanism, and you want STL to use your mechanism instead of the standard new and delete of C++, you can do that by providing a custom allocator implementation. This is quite useful in various cases, but here for our use case we will not be looking into it, since usually it helps if you want to improve the performance of your application and you have a lot of small similarly sized memory allocations, or generally just many similar memory allocations, so you could reuse memory blocks, but this would complicate things too much, and nowadays in the most cases this is not a improvement that one would need to do unless you really are implementing something really high performance, in which case you will need to look in many other optimizations on your own as well. Okay, the next type of map that we can take a look on are multi-map. So here for now what we can add is we could print out the map again, just so that we take a look how it looks, and we can take a look what happens if we try to assign an element multiple times. Okay, so key, this changes. First is the key, comma, second is the string. This changes here as well. Okay, so this obviously will be as expected if we just have the numbers that we added. 0, 1, 6, 7, 8, 9. And now we want to look what happens if we add, for example, another value as 9. And what happens basically is that we overwrite the previous entry. So the object that was allocated for this was deleted, and the new object with a new value has been created. The other one is no longer existing. And there might be use cases where you might want to store multiple values for the same key, and there are two ways how you can do it. One, let's say more naive approach would be to create a map which here as value doesn't have a string but has, for example, a list of strings. So this is another very powerful ability of STL, that is that you can combine those container types to create very advanced types which you can then use very freely in very many ways. Here of course now the assignment is not valid, so we need to push back. One thing that is a bit unsatisfactory about STL is that its default naming scheme for the built-in functions is somewhat not particularly intuitive. For example, one would just want to have a append and prepend instead of push back and push front. Why they did it like this? Well, historic reasons. It was supposed to be as explicit as it gets, so that you really know what it does, because append, one assumes that a thing is appended to the end, but it doesn't really state it. So append might also be appended at the beginning, so it's kind of ambiguous. Names like this, push back, push front, etc. are much more explicit. Okay, so here of course the next thing we need to get it somehow out, so we need to create another loop inside to access the second thing. For autoyot begin jot ungleich end jot plus plus, and now we print JC string. Procent S, let's comma separate it, and once we are done, let's just add a semicolon space. Yeah, and then now when we run it, it was of course a J here. As you see, it prints out 9 and 9, 9, so we have already found one way to add multiple entries to the same thing. But let's make it looking better. No, that will also look not great, because we always get the comma, and at some point we don't need the comma. We could of course fix that using some additional variables so that we can so that we know whether it's the first pass or not, so whether we need to add the comma or not. But I would say that doesn't matter for our use case here. It can be ugly. So let's see what's the other way of achieving a similar goal. That is a so-called multi-map. I think it should automatically include that. Multi-map. That will be then map 6. And we're missing the 9. And a multi-map gives us more abilities than a map. Did I delete the other one? I deleted, overwrote it. But depending on right. Okay, so just copy the thing before we modify it, and then now actually let's leave it here so that we have it here, and then let's create here a 6, and of course we use the map 6. Wait, this one will not be correct. This needs to be map 4. I copied on the wrong moment, and this we have also switched. Zack. Yeah. Okay, and we have here a multi-map. So if we use the square bracket operator, it will behave like a actually it doesn't allow us to use the so if we try to use the square bracket operator, it will not allow us to do it, because you cannot have like a multi-map behavior with this operator. It would always overwrite whatever is in the map. So we need to use a function to insert our value. This function can also be used on the normal map. It's called insert. But here a rather annoying thing plays in, that is that with the normal definitions in the STL, the thing that is held in the map is this pair object that we get the iterator for. So we cannot just add a key and a value, but we need to make a make pair, and then we can pass the two values to this thing. Other frameworks, like for example the Qt framework, have an insert which takes directly key and value, and let's just quickly check what other options here they offer us. I think in the newer versions of but we don't have it. In newer versions of C++, at some point they might add such a insert operation that will be more convenient. But for now, we need to do it by hand. And like the other inserts, we have like the other insert operations which we already have seen, it gives us an iterator out where the value was inserted. And with the normal map, not multi-map, it is slightly different, because the normal map gives us a pair instead of an iterator, where one value is a boolean telling whether an entry was added or an entry was overwritten, and the second value is the iterator. Here, since the multi-map always adds and never overwrites, it just returns always an iterator. So we have added, oh, we are missing one bracket. Integer first, map 6, and it's okay. And here we get our 9 and our 9 out of our test map. So it's quite flexible. You can do more or less both approaches depending on what you prefer. Using a multi-map might be slightly more streamlined and efficient, but then you are losing the ability to use the square bracket operator. With other frameworks, like for example Qt, you have also a map and a multi-map, but generally the one is derived from the other, and the normal map can also behave like a multi-map. So you can specify in the insert whether you want to overwrite or not, and then you might have multiple elements. And it always allows you to use the square bracket operator. Just that then if you have multiple elements, it will just access I think the most recently inserted one, which of course is super convenient in a way, but on the other side is ambiguous. So obviously something the more formal STL would rather not do. So with some frameworks, you might see that they are based on what functions they allow you to use, are designed to be more flexible, in the sense that it's easier to use them, but at the price that they are not so perfectly defined, hence somehow a bit more error prone, while the STL will be more cumbersome to use, but on the other hand it will not allow you that easily to make such mistakes that, for example, you assume that there is only one element, but at some point you use the other insert function and now you have two elements in the map with the same key, and then things start falling apart if you don't handle it correctly. Okay. Good. So far to maps. We have maps. More on maps. The next thing to take a look on will be smart pointers. So we had already something like a smart pointer earlier with our array, for example, here, although that's an array, not quite a pointer. But the STL has an own defined smart pointer, as we just need to include the right header. I think it's in memory. Zack. So there. Shared pointer, then it wants a type, let's say an integer. Per my int. Okay, and that's a smart pointer. And one thing, of course, you could try to do is new int. And you see, of course, here, interestingly, it doesn't like that. They could have added a constructor which accepts that, but I mean, they added a constructor, but the constructor is explicit, meaning that you need to do it like this, or like this. And both ways are not what they want you to do. What they want you to do is to stt make shared int Zack. And they're using the mechanism that we have seen already in the last lecture with the templates with variable arguments to pass the construct argument. So if this would not be an integer but something more complex, when here we could pass basically any amount of arguments, then which would be then passed directly to the constructor, which is then called by make shared. So this is quite flexible, and this gives us a pointer which can be easily copied. My pointer 2, and once the last instance of this pointer gets deleted, only then the int really gets destroyed. So let's create maybe a quick test class. See my object. Name. Let's want a destructor. Capital N, just for correctness. Oops, if you know that you are always overwriting a value in the only constructor you have, it's fine to not initialize it in the header like here. But just to be sure that you never forget it, it's better practice to always initialize values, even if you do that later. Do you overwrite it later on? F %s, comma. We have our constructor. We have our destructor. Name object1, because now here it complains because of the type. Okay, so let's put this here, put this in a scope, put this in another scope. Wait, this is not correct. Yeah. Okay. Put the breakpoint here. Run it. Oh, we forgot the new line. I think that will not make for any good readability, so let's quickly fix that. Okay. Let's move it so that we can observe it. So we had the constructor. Here we make a step. Steps are hidden. So the object is maintained, and only when we exit the last scope the object gets deleted. So we can create as many pointers to the thing as we want, and it will maintain an internal reference count, and only once the last reference goes out of scope it will delete the object. So this helps greatly to reduce various memory related issues, and when you're writing modern code you should always use some sort of smart pointer. Older frameworks like Qt bring their own pointers, smart pointers, which behave similarly. Much newer frameworks would just try to add whatever is still missing in the STL, so you would just use the STL pointer type in those. And pointers have the nice property that they can be either as a normal shared pointer, so it's called a strong reference, or you can create a pointer which is a so-called weak reference, weak pointer. And the weak pointer has the property that it kind of holds a reference to what it points to, but it doesn't prevent the element from being deleted. So let's see, if we go out of this bracket the reference will be deleted, and then the smart pointer will no longer work. So what we can do here, so we have here our weak pointer, and we need to keep this here, so let's add yet another reference for. Okay, so when we go here outside this thing, since 2 holds a reference, the thing still exists, so we can make 4, and then we take our weak pointer, and it has the log function, which will increase the reference count and return us a valid shared pointer, or it will fail and return us a null pointer. So there, after doing this operation, we always need to check whether this thing is null or not, and it has an operator, so if then my object, and then we repeat. Actually we can just move this down here, and then we repeat the same thing. Semicolon is missing here, and this will be 5, and if it's alive, else okay, you can run it, And we again forgot the new lines, but we see that the first thing said that it's alive, then it was destroyed because those thing went out of scope. And here when we tried to do the same thing, lock on our pointer, on our smart pointer number 3, it said that the thing is dead because it well was no longer existing in the memory space of our application. So such strong and weak references are extremely useful in various use cases. So if you would have, for example, an object which points to something, and that something points to something else that points back to the first object, then you would end up in a situation where the mechanism of deleting unneeded memory of a smart pointer as used here would fall apart, because always something has a reference and there is no way for this mechanism to know that this is a sort of circular reference, and it then ends up never freeing the memory, which is not good. Other languages which have a garbage collector like C# or JavaScript, they don't need such a explicit differentiation between strong and weak references, because there the system will suspend the whole program from time to time and then inspect all the dependencies and references and find such disjoint circular references and also dispose of them. But this gives some unpredictability to your application's behavior, and therefore is not always what you would want. C++ works much simpler, much more direct, but at the price that you need to still take some own care, even when using smart pointers, to at least ensure that the memory will be properly released. So in this case, for example, what you would do is that you would use as one of those references a weak pointer. A typical use case, for example, would be you have some object, some sort of tree structure maybe, where you have some root element and a branch and some leaves, and then of course your root is pointed to by some pointer that you hold somewhere. It has a list of branches or leaves, which then are normal strong pointers to those objects, and so on until you arrive at the leaf. And in many cases, when you are operating with such structures, when you get one of the objects, you would like to get its parent. For example, if you want to remove it from its parent, or if you want to add something to its parent, or for whatever other reason. And here, if you would be using such a strong reference, then of course this would be a circular reference, and then the memory would never be freed. But if you use a weak pointer to point to the parent element, then such a behavior is avoided, and it also makes sense that if the parent object gets deleted, that all the child objects, unless they are referenced from somewhere else in addition, will also be deleted, while on the other hand, removing of a child object should have no bearing on the parent object. So that would be, for example, a reasonable use case of this strong and weak pointers. Is everything clear so far? Are there any questions? Pointers, and especially smart pointers, are very important to properly understand, since they are an important part of the safety mechanisms that are available in C++, and they help avoid many classical C++ errors. Okay. If there are no more questions, to this, if everything is clear, then let's continue. So one thing that for this we will create a new project. Create new project. C++ console. Multi-threading. Wait. So everything that we have done until now was always happening in the main thread of the application. So we had like one sequence of things that gets executed in order, and this is quite easy to understand, let's say, and it does not offer that many opportunities for even more exciting bugs. but of course doing everything in order one by one is not always the most efficient way. Usually it's good to do things in parallel, so try to start as many workers as possible, and each of them will have some of own task to accomplish, and as long as these tasks are not dependent on each other, this will speed up your completion of the whole operation significantly. When you think about modern CPUs, come with even up to hundreds of CPU cores, and if you have one thread, you can only give something to do to one single core, so that is really not very efficient. Even on modern phones you have like 8 cores or something, so it is usually a good practice to, whenever possible, try to split the tasks in your application. So basically what you're doing is you are starting multiple parallel threads of sequential executions of things, and the way this works in the simplest way, let's first look how this works without any STL or anything. In this case, it will be Windows specific. There's a function create thread, which takes quite a few arguments. The first argument will be this one is important. So we'll copy. Yeah. So back to our function. So the first argument is a security attributes for which we don't care. You can just use it null. The next will be the size of the stack. So what we do is we just specify 0. Then Windows will take the default stack size. But in principle, we're creating a thread, and if you would know that you need more stack space than is default on Windows, then you could create it and tell the operating system that for this thread you want a much bigger stack. And then we come to the sorry, my voice is not working quite well today. We are coming to the thread start routine, which is pretty much just an address of a function. And like main was the entry function for a program, where there is stuff that happens before it, but not stuff that we would have programmed, so we don't care about it. Here, the function it will specify will be the entry function for the thread. So I copied earlier the right function prototype, at least a part of it. So it returns a double word, and let's call it my thread. And it takes a LP void, which is a precursor macro for void asterisk. Also, this far and near, you can just ignore it. That had a meaning ages ago with old APIs, and it is left within the API of Windows. But if you go with it, just defined as nothing. It just, if you would be building a 16-bit application, then they would be meaningful. But modern systems cannot even execute 16-bit code anymore, so this is really irrelevant. Okay, so this is just, let's just for simplicity write void asterisk so that we know what it is. And this Win API is a function calling convention, as you might remember from our lecture about functions. On a 32-bit system, that needs to be correct. On a 64-bit system, it doesn't matter, because there only is one calling convention in reality used, even though there might be some different specifiers defined. So here, but here we leave it just for correctness. Okay, so we pass here, our function. Then we can pass a parameter, which will be passed to our function here, so which is quite useful. So let's create a structure as my params. If it would be like just one value that we want to communicate to your thread, of course you would not need that, but you might want to give it a string and an integer and a list and a map and whatever. Then what you would do is you create a structure which has those arguments. Let's say int arg1 0, and for now let's just leave it at that. So params, let's create new params that needs to, of course, asterisk. that needs of course to be a pointer, so we need to create a new one. At this point, unfortunately, we cannot pass a smart pointer because we can only pass a normal object. A smart pointer would already be more complex. So unless we would create some own wrapper for the thread creation and thread starting, then we are here limited really just to the basic machine types that we can pass through this param. But if we do it correctly, then there is no risk of breaking things. So this is a common practice. Then we have creation flags. We can specify a few things like create suspended. Some of the flags are valid generally, some of them are only valid for threads. Some of them are valid when you're creating a process, some of them are valid when you're creating a thread, like create suspended works for both. And this would mean that the thread will be created but will not start executing code. For our use case, we don't want that, so we just go with 0. And then we can specify a double word argument to which we will receive the ID of the thread that was just created. This ID is needed if you want to open the thread from another process, or if you want to open the thread again for whatever reason. But in our use case, we'll just pass null here because we don't care for this ID, since the thread here also returns as a handle, so it is already opened for us. The handle, when you investigate it at some point, it's again just a void asterisk, but it's not a memory pointer. It's a number which identifies within the kernel this thread, and often also just within the context of the current process. So usually handle values, on Windows at least, are not unique. So if you have an object which you have created a handle, if you want to give a handle to another process, you need to use the function duplicate handle, and it will create a new handle in the target process with a new value. But inside the operating system, all the values will still point back to the same internal object of the kernel. So here we have our handle, and an important thing is that these handles need to be closed, otherwise the object in the kernel will never be dereferenced. So when a thread starts, it starts doing its things. So it starts here, it blah, do something, bloop, and then return. We need to return a value from this function. Let's say return 0. And what you might want to do is you might want, for example, to wait until this thread is finished, or you want to find out which value the thread has returned. And all those things can be done using this handle. And the idea is that as long as there is at least one handle open to this thread object, some data for this thread, even if it terminates execution, will still be maintained in the kernel, like for example the exit code. And thus, if this handle is not closed, those data will remain in the kernel for the foreseeable future. In practice, of course, once the program as such gets terminated, then all its handles will be released for it. So if you write some super quick tool that just does 3 things and then exits, you will be fine by not freeing the handle. But of course, this is not recommended, since if you would adapt the code for a program that would then be supposed to run indefinitely until the user exits it, then it would start accumulating handles, and at some point, like with memory leaks, the resources of the system will be exhausted and things will start crashing. So to avoid that, we use the close handle function. Once we are done with this, here in our use case, we will just we should not close it instantly, we should wait for it. So wait for single object handle. You can specify how long to wait for. So in our case, we want to wait forever, so we just use -1, so say infinite. Preprocessor definition, which again is just int32 -1. And if you specify something, then it will be in milliseconds. So you could wait for up to, I think, 44 days and a few hours. And that's the biggest value you can wait by, which kind of makes sense. And of course, you could like put it in a loop and then wait again and again. The wait for single object will return you values and tell you how it stopped the waiting, because the waiting can stop due to multiple events. So it can stop once the wait condition have been satisfied, obviously. It can stop because the timeout was reached, which is another scenario, or it might also be kind of forced to bug out if you would call close on the handle. So if you would close the handle, then things waiting on that handle would also be triggered. And depending what happens, you will get a different error code. So for success, you get wait object 0. Oops. Which, if you look into, is just the number 0. No, it's wait status plus 0, but wait status is, I think it's 0. Yeah, it's still 0. And the idea is that there is also a second function called the wait for multiple objects. So basically, it will then give you a value like wait object plus 1 plus 2 to tell you on which of the events that you wanted it to wait it actually has reacted. Then of course you can get a wait timeout. These are then special values. So for example, also see here that you cannot wait at the same time for I think more than 256 objects or something like that, because then you would already arrive at the range of valid exit codes. So wait for timeout. That would be when the timeout is reached, and you would also have like wait failed when something really bad happened. I think that's just -1. And you can also have like wait. Oops. Wait aborted. Which also indicates that the condition was not met. And usually here you look what of those things happened and then take an according action. Or if you don't care, you would just then close the handle and exit, which is also fine. If you want the exit code, what was it? Get exit code thread. As you have seen, there is also a get exit code process, which gives us an exit code for a process. So when you create a process, then you can also wait on it, and then you can also get its exit code. The exit code will be whatever the main function returns. And here this thing can of course return 1 or 0, meaning success error, and it will give you a, and it will wants a pointer to what? Let's see, 0, into which it will on success write what happened. And on failure, for most functions from the normal typical Windows API functions. So on Windows there are like 2 levels of functions. There are the Win32 functions, which are provided by the kernel 32 DLL, and later some other DLLs like user DLL, GDI DLL, etc. Which were present as such in Windows 95, 98, Millennium, and so on, and of course in any modern later Windows here. But Microsoft have recreated at some point the kernel of Windows, starting with Windows NT, and there you have a separate DLL which actually takes over the communication with the Windows kernel, the NT DLL. It's called just ntdll.dll, and it has and the function calls which this DLL offers are considered native Windows calls, and everything in all the other DLLs, which is not, unless it's related to the graphical subsystem, this is again a little bit different, but everything from kernel 32 and so on, all those function calls are always translated onto ntdll calls, and those work quite differently than the normal Windows API. We will not be looking into it, I think, during this lecture. That would be too complicated. It is just good to know that on Windows there is this dichotomy between the native calls and the calls which you would natively associate with Windows. So for example, one thing that you associate always with Windows is that you have drive letters, and all the paths start with a drive letter, while for example on Mac you don't have that. On Linux you don't have that, and in fact the NT Windows kernel also does not natively use drive letters. It uses NT object paths, which start with \device, \hard disk, volume1, etc., etc. And it uses an internal mapping such that it can map drives to paths, of course, otherwise the whole thing would not work. But the thing is that you could, in principle, for every user on the system, have different drives mapped to different physical devices. The one thing about this NT paths, which is a bit annoying, is that they are dynamic, meaning what is hard disk 1 will depend on the order you plug your hard disks into the system, or on the order they get enumerated on the bus. And so, for example, if you have some device attached and you reboot, and then you reboot again without this device attached, all your NT paths will shift accordingly. So you cannot save them and refer to them across reboots. If you would want to use NT paths for anything, then you would always need to map them yourself back to drives or to drive serial numbers or something. Thus, obviously, on Windows, everyone is just using the drive letters. Here, the operating system takes this mapping function for you, and is quite convenient. But I think it's just good to know that on Windows, there are things which behave a bit more like one would expect them from the Linux world, and this drive letters, which came from DOS and all the operating systems, is something that's kind of plugged on top of it, but it's so omnipresent that it kind of feels native, even though it is not. Anyhow, what I also wanted to say is that most of those functions, if they fail, they will just give you true or false, or an error value. So, for example, create thread, it returns a handle, but it might fail. So what if it fails is it will return a so thread is equals invalid handle value, which again is a special value, in this case just -1. And if it does this, then we can bug out, because it means it failed. Or like this function that also just gives you a very unspecific error code. I mean, this one gives you actually quite specific error codes in the grand scheme of things, because it is more than just true or false. This one just gives you true or false, and all those functions, they will set on the calling thread in the thread environment block a variable with a more verbose error code. So if something happens like here, you can always call the get last error function, and this function will you get a word, which will then describe what which will be much more descriptive. It will say like access denied, invalid parameter, memory allocation failure, whatever. There are literally thousands of error codes, and you can look them up. You can, for example, Google just for Windows get last error codes, and then you already get to the Microsoft page describing those. And this function works for most non-native Windows functions. The native Windows functions, they usually return always status, so they just directly return you an error if an event occurs, and the success case is if they return 0 or a positive number. There are some other Windows APIs which might not set this last error, but most do, and unless you are working with the native API, you usually can rely on there being a get last error, and you can just look it up what it was. There is an interesting exception in case of network functionality. The Windows sockets have an own VSA get last error function, but at least on all the recent versions of Windows, at least since 7, probably since Vista, even if not even earlier, it's just an alias for the normal get last error. So at some point on Windows it was a dedicated function which apparently worked independently, but at some point they just unified it, which is good. But you might find code which will explicitly call a VSA get last error instead of, or was it get VSA last error, one of those, instead of just a normal get last error function. But it's good to know that internally this will still be the exactly same thing. Okay, so we have here return code. We waited for it, so let's just make it do something. So for example, we can int x is like null, for int for int x is less than 900, or let's do it int is like null, is less than 900 e plus plus, and x plus is equals e, and return x. Of course, what you also could do is you could have here an additional parameter on which you return some more complex object, and then after you wait it and you know that thread is done, then you can refer back to your parameter and do something with it. Oh, and of course here we have forgot to clean it up, and let's make it a bit more useful. So let's give this a value, smaller value, and then we clean it up. And there are two ways you can handle this. You can either care yourself for cleaning it up, or you can make the thread clean it up on its own. And of course now we need to be able to use it, so we just cast the thread param to our type, then we can do things. And here, so that this is not done instantly, let's add the sleep call. The sleep function suspends the execution of a thread for a specified amount of milliseconds, and then it resumes automatically. So for example, you could make a thread which wakes up every minute, checks something, and then goes to sleep back again. And as long as it's sleeping, it is not consuming any CPU time. The operating system's scheduler just has a note somewhere that this thread should be woken up at some certain clock cycle, and then it will do it. The internal mechanisms would be too difficult to explain in detail. So what we do here basically is we start the thread. The thread will wait for 100 times 10 milliseconds, so for about 1 second in total, and each time it will add the I to x, and then x will be returned here as our return code. A somewhat annoying limitation here is that these return codes are 32-bit, meaning if you have a 32-bit system, you could return a pointer to valid memory and do something with that. On a 64-bit system, I mean, you could like try to force memory allocation in the lower 4 GB and then return that, but that's a really ugly hack. You shouldn't do it. So if you want to return something a pointer like, you necessarily need to do it through this myparams structure. Yeah, okay, so let's run it. Well, that will be a bit boring. Let's put a breakpoint here. It starts, it runs, it waits, and it's done waiting. And we got an exit code of something which looks reasonably large, so that it probably did what we wanted it to do. And the important thing to know here is that now both threads are running in parallel. So we could, for example, start a few more of those threads. We could here add more arguments. So let's the arg2, which is 0, and that will make here my thread 2, let's say. And let's say the thread, one thread will increment arg2 and the other one will decrement arg2. Although this is kind of that will not to demonstrate the potential issues that might arise here, we will remove the sleep, and we will make it to run for like 1,000,000 times. Okay, and this one will increment arg2 plus plus plus, and this one will decrement arg2 minus minus. Then we create a second thread, thread 2. Oops. Handle. Right. So we could wait for multiple objects now. And the thing what it needs is it needs a count, and then it needs an array. So the modern way would be to create a vector and then push things back and use the vector's count. But the old school thing is just a normal C-array handles a specified size h, comma h2, and bear weight all. I think it will be false. You can specify whether you want to be triggered when all events are met or when any of the events are met. So in this case, actually no, we want to wait all. We want to wait for both of them to finish. And once both finished, then we can printf. Of course, we cannot dispose of this anymore because we are sharing it and we want the value. So we no longer dispose of it. Of course, we still want to dispose it once we are really done. And we of course need to also remove the second thread reference thread handle. We don't care for the return value of the other handle for now. And here we can just now printf. Printf wants an include stdio printf params, what was it, arc2 params arc2 %d equals %d comma arc2. Okay, let's run it. And depending on many conditions, the behavior here might be different, but we see here, for example, already, so it finished quite quickly, that this is not 0. So we would expect, obviously, if we increment the value 1,000,000 times, and if we decrement the value 1,000,000 times, plus 1,000,000 and minus 1,000,000, you are still broke, 0. But the value was not 0, and in fact, each time we run it, we'll get a slightly different value. If that would work with money, that would be fun, but unfortunately it doesn't. Actually, I think even had a negative value here, sometimes. So how can this happen? It happens because the way this works is that those two threads run. They might run in parallel on two different cores, and the cores might cache memory. So effectively, the one thread which last flashed his value to memory wins. And which thread this is random. As we have seen, more often the plus thread wins, but sometimes the minus thread wins. And well, obviously in computers, unless you have a random number generator in hardware, nothing is really random. Here it's like with chaos theory. It isn't random, but we don't know everything we would need it to know to make a prediction. So for us, it looks random. In this case, all the other threads in the system that run, hardware interrupts which happen, network traffic that goes in, all of those events will influence the scheduler, make threads wake up, make threads go to sleep, etc., etc. And at some point, this is just too complicated to predict which thread will win. So obviously this is a problem, because you might, for example, want to share a list. For example, you would make, let's say you have 10 files, and in those 10 files you are looking for something. And since you have an SSD, you can search in the 10 files in parallel. So you would start 10 threads, and then you want to all of them to write into a list if they found what they were looking for. And then, of course, you don't want a situation where two of the threads find something at the same time. They put it into the list, and then only one entry ends up in the list. Technically, if you are using a STL list, that would be even worse, because concurrent write accesses to the same object will probably leave the memory in an inconsistent state, and the thing will cause a crash. So that needs some sort of remedy. One thing that with very simple variables can be done is define them as volatile. I think long was it. This as such does not make it enough, but at least volatile tells the compiler that it should assume that this can always change. But what we really would want to do is to use a atomic instruction. It was interlocked add to increment volatile long reference param 2 arg. So interlocked add and we need to say what we add. We add 1, and then we have interlocked subtract, I think. Subtract, maybe it wants a negative value. I think there is no dedicated function. It depends on what platform you have, which of those functions are available. But we have different bit sets. Increment. We have increment and decrement. This is by 1, but we only have add. We don't have a subtract. And since the thing works on signed longs, then it works just fine to specify it in negative value. When we run it now, oh, that didn't work. Wait, why? Oh, that's why it didn't work. I forgot to comment that out. When we run it, suck 0, and it will be 0 each time we run it. Suck, suck, suck. The way this works is this interlocked operations, as we have seen. There are quite many others, like you can have increment, decrement, bit sets, and or XOR, etc. Most very useful interlocked compare exchange. Those operations are executed in hardware by the CPU, so they don't require any invocation of the operating system, and they still allow you to synchronize access to memory. So on the hardware level inside the CPU, these instructions are implemented such that when the instruction starts doing its thing, no other instruction can jam in the middle of it and do something. Naively, if you have just a plus plus or minus minus, and if you'd run on a system which only has one core, then you would kind of think that at least there it should work, right? Because there is one core, plus plus or minus minus should ideally be a single instruction. But of course, in reality, as we have seen code, it might be the compiler may make from it load value to a register, increment the register, store value back to memory. And if it does this, it's actually 3 operations, and the operating system scheduler can preempt those at any point. So really, you'd never have guarantees that something will not be preempted somewhere in the middle, even on a single core system. That is, unless you are using such atomic instructions as specified here, because they in hardware will ensure that the operation will be executed to completion and nothing else can interrupt it. Since, of course, the way the operating system scheduler works is it can only from one instruction to the next instruction, specify an interrupt, and thus, of course, there is no granularity for the operating system to interrupt such an operation. And even if you have an operation which internally is made of multiple steps, like, for example, the compare exchange, which compares whether the value in the memory specified is equals to a given value, an expected value, and if it is, it will replace it with another given value, and if it is not, it will return a failure, or it will return the previously defined value, and then you can deduce yourself that apparently it didn't work because it wasn't what you expected. And even such multi-step operations cannot, even if they would start on 2 cores at the very same time, the CPU's hardware has an arbitration protocol how those cores ensure cache coherency. That is that at any point in time, only one of the CPU cores can own a cache line, so a set of data for writing. And a cache line can either be owned by one core for writing or for multiple cores for reading. So as soon as an operation is started, which is supposed, for example, in this case, to increment or to add, to be very exact, add the value 1 to our variable, the CPU will request exclusive access to that cache line, and then all other CPUs will evict their copies of the same cache line from their caches, since every core has its own at least L1 cache. L2 cache can be shared, and L3 cache can also be shared. So those cache lines will be evicted, and then the one core will, to completion, complete its even multi-step operation, at which point it will release the cache line so that other cores can read from it, and the operating system cannot interrupt it. This way, it is guaranteed that these atomic instructions will always, even on a multi-threaded system with multiple CPUs, work, as the name says, atomically. There is another mechanism that can be used here. Obviously, this is kind of very basic, so one would, for example, wonder how one could access an STL list, for example. We mentioned lists before, so how one would do that. So we can do this, we can implement it. So let's include hash include STL list. Then we create here a new variable list int, and we call it found std, and we'll be looking for something. Doesn't really matter for what. This we can comment out because we're not interested in this anymore. And then let's say if x modulo 1, 2, 3 is 0, then we found what we are looking for. Doesn't need to make much sense, just has to be something. And the breaking case would be, of course, to found. Not found. First, we need, of course, a parameter. Found push back x. And if we run it like this, it might crash and will definitely not contain all the valid results. Let's run it. Actually, it didn't crash, huh? We were lucky. Do we want to do something with that? No, that's fine. We could here want to print everything, for example. No, that printing will take too long. Let's just go through the list. So for auto f params found. Let's not do anything with it. Let's see if we even can just iterate through the list now. It might. Okay, it doesn't crash. That is fun, but as said, it should. It is not safe to do this. If it doesn't crash, it's just we are lucky. Can we make this? Okay, let's do it differently. Let's pick something that will most certainly crash. So the thing with the list is that it just really adds to the last element, and if you are lucky, you can avoid problems. But if we go with a vector, it will need to grow the vector. It will need to make operations. It will hold memory references. It will take time. That most certainly will crash. Or it will. Yeah, it crashed. Suck. Here, something with memory allocation. Delete. Apparently, we tried to delete the same block, the same memory block twice, as part of here change array. So, as you see, and this is by the way one of the very dangerous things of C++. Sometimes things might just work even though they are completely wrong. With the list, you have the same problem, but since the list only always operates on one element, the likelihood of such an bug to be triggered is low. So you might have a situation where your application, for some of your users, will crash in some very odd situations, and you cannot reproduce the crash. And this is why it's very important to always try to do things the right way and not the it works and it's fine way, because you might end up with bugs which are extremely hard to hunt down. With the vector, instead of the list, we used it such that we triggered the bug quite quickly. But if we would have, for example, here the sleep still in, it is quite likely that even using vector would just work until it stops. So it's important to know that C++ is kind of dangerous in this way. So how do we solve this? Well, one way, of course, to solve this is to have a variable. Let's call it in use, which just tells us whether the thing is in use. And ideally, of course, when we would want to set it to a value, and when we are done to set it back, and first, of course, check whether we are allowed to use it. As we have seen, we cannot do it with just a normal operation, since those are not atomic, so we will need to do it with an atomic operation. So we will use a if interlocked type interlocked compare exchange. Okay, so our destination is our params. Oops, that was in use, comma. Then we want to exchange it with 1, and we want to check whether it's 0. so 0. And if I recall correctly, the function should wait, it does look like something this is missing. The function should, I think, return the last value that the thing has. So it returns the initial value. So we will check if this is 0. So if in use is 0, then comparison with 0 works, and it will be changed to 1, and it will return the 0 that it was before it did the exchange. You could have also interlocked exchange, which would return you the initial value, exchange it to a new value unconditionally. But that would not work with our use case here. Here we want this compare operation. And if this is 0, then it's fine. If it's not 0, then it's not fine. So what we can do is we can switch this from a if to a loop. While this is not 0, sleep for a millisecond. And then of course so once we arrive here, we know that we now own the in-use variable, and we can do with found whatever we want. And once we are done, we just we just use the interlocked exchange. We know it's 1, we don't need to check anything, just reset it back to 0. And then we just copy this to our other place where we are using it, and voila, we have created a self-made synchronization mechanism. This thing is called a spin lock, because here when it's trying to acquire the lock, it's spinning and spinning and spinning and wasting CPU time. It's actually quite already in a way an advanced spin lock, because it actually can sleep. If you would create a spin lock somewhere in the kernel, it might actually really just like spin and burn CPU time at full blast. So let's run it. And well, it didn't crash, so it works as expected. We probably want something here. Let's say like printf param2 found %d found size, so that we just have a feedback that it finished successfully, and it found well 19,360 numbers which are divisible by 1 to 3 without remainder. And actually it did it twice, since we had 2 threads doing the same thing. We could of course make it like give them like different start parameters or something, but that doesn't matter. For the demonstration of the mechanism, it doesn't count. And as you have seen, it was almost as fast as it would be without this sleep. But if you would do something really time critical, you could really make the spin lock spinning at full blast without any sleeps. It works just fine. The problem of course is that while this thing is spinning, it is wasting CPU time. So such a sleep, if you can afford it, is good to have. And of course this method is very manual. So usually on Windows you would use other mechanisms to synchronize. So this mechanism, as demonstrated here, is something that you can use on any platform, more or less. So the CPU of course needs to support this atomic operations, otherwise it won't work. But any x68 CPU does it. ARM CPUs do it. It's maybe not always the exact same complement, but the most important ones like compare exchange, increment, etc., they will all support. You know, maybe some extremely old, like an 8200, like a 286 or something really old, that might not be able to do some of those things, but that's like 30 years ago technology, so it's kind of irrelevant by now. So all the modern things will do such things. With microcontrollers like Arduinos, that's a different story, because they are usually not made for multi-threading at all, and they only usually have just a handful of instructions. I mean, they have to be like a penny per chip, basically, if you buy a larger quantity. So there, they probably most of them don't have any sort of atomic instructions, etc. But things which come in the category of system on chips, like Raspberry Pi, Raspberry Zero, those things, all the clones of this Raspberry thing is the BeagleBone, Banana Pi, etc., etc. They all, every modern Android phone, those all use system on chips, which pretty much means it's like a whole computer on a chip, and it will have all these advanced features and will expect a proper operating system with threads to run on it. So the instruction sets will contain such operations. Also, to some extent, if you are compiling for a particularly old platform, if the thing has a CPU, if the thing has an operating system, you are not programming for the bare CPU, then the operating system can emulate some of this functionality, just that it is extremely expensive computational wise. So first thing we can do is we can take a look how such emulation would be done. So we would not use this, instead we would use a handle mutex equals cal. Zack, we will comment this out. We'll comment that out. So if we want to use the operating system, obviously the operating system needs to know that we want to use it and it will need to create internally an object that will help us. So create mutex. You might, by the way, with many Windows functions see this, that actually it gives you a name with A and with W, but if you use it without a name it also works. And if you look into the definition, you see here that the A is like the ASCII version, V is for white string, for Unicode, and nowadays you always should use the V version, the W version, or you can just use the preprocessor macro that will pick the right version for your project, but pretty much any modern project is configured. What was the language? Unicode. What was that? Yeah, here. No, that's not the right one. Summary is a setting where you can select between Unicode and not Unicode. Oh, actually, maybe they have removed it in the modern versions of the compiler, like the super old ones, Visual Studio 2002. I mean, there you had such settings, but it's like almost half a century ago already. So by now, pretty much everything is just Unicode. But those APIs still exist for compatibility reasons, because you still can run applications made in the last millennium, so they will be there for the foreseeable future. Okay, so here again we don't care for any security descriptor. Initially own false, so it should not be locked, and we can give it a name which we don't want to, so null. If we would have given it a name, any other program in the whole of Windows using this name could access this mutex, this object. This is why we would here want to specify some security settings, so that we could say only administrators can do it, or only a certain user is allowed to do it, or only the system, etc. But when you operate within one application, obviously this is not needed. First of all, you can just duplicate the handle if you would want to, but in the same application you don't even need to. You can just copy the handle and have multiple things refer to the same handle instance. And of course, before we forget it, we should of course close handle the thing. We don't want resource leaks, so we have here this mutex object. Mutex is kind of a shorthand for mutually exclusive, and interestingly enough, in the Windows kernel, the thing internally is called a mutant for whatever reason. Okay, so we have our mutex, and here we want, what was it? Was it log mutex? One moment, I need to look up the right syntax. Like everything, of course, will have different names. Log. Log. See, the log mutex or acquire mutex or something on this on these lines. So to release this is release mutex. I think it's wait for single object. That's also possible. If I'm not mistaken, you lock the. Really, that is strange. Yeah, definitely. Okay, so you lock the mutex using wait for a single object. That's a design decision worth forgetting. That's why I forgot it apparently. And you can specify for how long. So like with the other wait for single objects, you can specify that you want to only wait a certain time and then maybe bug out or something. And here, of course, we could count the loops and say, okay, if we have waited for 1,000,000 iterations, then we just bug out because apparently we are not going to get our lock. Okay, so we have here our things, and to release it, so basically the reset to 0 is release mutex. And then of course we copy this and do it twice here. Zack. Okay, let's run it. And since we have only 2,000,000 operations, we don't really see a speed difference, but this operation, since it's each time invokes the operating system and has transitions from ring 4 to ring 0 and so on, it will be extremely slow in comparison to our self-made spin lock. There are advantages to using a mutex. That is, the mutexes have certain guarantees. For example, with the spin lock, there are no guarantees. Or rather, there is only one guarantee that if we get it, then we have it. But there is no guarantee in which order we will get it, when we will get it. So if you would have, for example, with 2 threads, it kind of doesn't matter. But if you would have like 100 threads, which all are trying to obtain the same lock, if you use a spin lock, which thread obtains the lock will be more or less random. So one thread might wait forever and ever and ever, and then wait some more and last get the lock. While with mutexes, you have guarantees that the access to the waiting objects will be somehow fairly distributed. So we will not. So you kind of have more predictability with regard to your operations than with a simple spin lock. The downside, of course, is the amount of computing resources that go into it. The Qt framework, for example, the way it is implemented is it mixes a spin lock with a mutex in a very clever way. So it tries to obtain a lock, and if it's successful, well, great. If it's not successful, then it will set up a mutex object, or rather as a type of event object, which is similar but not quite the same, which then will be triggered, and then it will wait on that event. And this event will be triggered by when the other instance of the Qt mutex is released. So the thing, when it releases, will check whether it will not just use a simple override, but it will look what is the value currently in this atomic variable. Is it like, because there will be like a special value for not acquired, so free to use, a special value for it's locked right now, and then it can be not one of those special values, but a handle to an actual event. And if it finds this event event handle value, instead of the placeholder for it's in use, then it will trigger this event after it has reset the value to 0, which will then wake up one of the many waiting, if there are many waiting, or the one waiting thread, which will then acquire the lock. The other ones will either not be woken. So with events, you can have multiple threads listening on the same event, and when you are setting an event, depending on the implementation of your event, you can specify like wake one or wake all. And obviously, in case of this mutex usage, you would go with the wake one approach. While in other scenarios, if you have an event, you might want to wake everyone that is waiting for it. So this way, you get, if there is no contention for the mutex, you will get a very fast performance, because it will just use the hardware instructions, no transition to the kernel needed. But if you have contention, so there are multiple threads wanting to get some access, you will not send those threads into spin loops, spinning and wasting CPU time, but they will then gracefully just start waiting, and then the operating system as a mediator will be invoked to wake them up and so on. And since this is such a helpful improvement, there is a Windows native way to also have some sort of a smarter locking mechanism. It's called a critical section. So let's create one. Wait, we need to comment out more things. This needs to go and this needs to go. Okay. But before we start with that, is this clear? Are there any questions? So the synchronization is an important topic, as we have seen improper concurrent access to a resource can not just crash your application, but leave it in a inconsistent state, which might of course cause crashes further down the line. And the main issue there is that such bugs are really hard to debug, because something is broken, and in the moment when you find out that it's broken, then the thing that broke it is might be long gone. Okay, if there are no questions, then let's try the next synchronization method called the critical section. Create sect. Okay, that thing, of course, like all the other things, needs some initialization. Initial sec critical section. That wants a pointer. And that's of course wrong. Params. Critical section, and then of course we need to get rid of it, and it will be delete critical section. And when you look on the function, there is also a create critical section X and spin count. So internally you can specify additional parameters. So first version was just end spin count, and then it was end spin count and flags. And the idea is that if you have some contention for a resource, it might not be the best thing to invoke the operating system from the get-go. So maybe it's more effective to spin 1 or 2 times and then say, okay, I'm not getting it, so let's go the complicated route. And this is what this critical section does. So obviously we need somehow to enter it, so enter critical section. Let's copy that from here, and then when we are done, of course, leave. Oops. Leave critical section. And we repeat it, we run it, and it will also work correctly. And now, of course, the implementation details are not transparent, since this is a something Windows internal, and Windows is not open source. But we know that it is implemented in the kernel 32 library, and that it somehow ultimately will implement some sort of a primitive that uses a spin log, counts up to a value, and if it doesn't get the log, then it will create some mutex or similar object and wait internally and then release. One could of course try to get into this, disassemble the file, take a look, but that's not really interesting for us, since we can just use it as is, or use Qt's implementation, or write an own implementation. As we have seen here, it's not that difficult to combine such a thing with a mutex. One thing, of course, that is important is to always release the resource, because if we forget this, let's say we have forgotten it only in one thread, if we try to run it, then our application will get stuck and be there stuck forever. So when we inspect the application with a task manager. Where is it? Multi-threading threads. Okay, then we have yes, we have the main thread. No, we don't need this. We don't need that. So we see here the main thread is waiting in a wait for multiple objects, obviously, since we put it there. Then we have the next thread, which is wait. This one is let's pause this for a second so it doesn't change. So this one is our main function, which waits. Oh wait, is this version? This version is broken. One moment, please. This version of the task manager is broken. Where's the newer one? Task Explorer installer release. Which one was it? Oh, this is not old. There's the right version. It has a bug that once you select a thread, it will always show the same stack trace for all the threads you select from the same process. We should have exited it. It will also complain that it cannot overwrite one file, but this always happens. This is just fine because that's a driver for the Windows scanner which cannot be unloaded once it has been loaded. So we would need to reboot the whole system to unload it, which we don't want to. Okay, multi-threaded. Suck. Okay, so again, we have here our main thread. And then we have one more thread which is stuck in my thread 2 plus some offset. It actually even tells us if the debug had the PDB file is available, even in which line it's waiting. Of course, for the Microsoft files, we don't have this information, so we don't know that. And then, of course, we have here the enter critical section, and then it's stuck. And it will be stuck there forever until we kill the program. The reason is quite simple, because the other thread entered it and it never left it. So if we would have forget, oh wait, this was not the right one. Here we forgot it. The same behavior would get if we would have forgot to release mutex or forgot to set this back to 0. There are certain caveats. You can have mechanisms. So for example, here we have seen that one of the threads terminated. So if we would forget this or forget that, both threads would stack and be stuck. Critical section is defined as recursively enterable, meaning that if you call enter critical section on a critical section inside a thread which already owns the critical section, this will not trigger a wait event. It will just increase an internal entry counter. You need to call a leave critical release what was it? Yeah, leave critical section the same amount of times as you call enter, but in the same thread you can enter it multiple times, which is quite useful. Because imagine a complex object which has various functions. If you need to lock some resource and you have and you don't have a recursively enterable synchronization mechanism, then you would need basically to have like all the functions in a version which don't lock anything for internal use, and then wrapper functions which just lock the resources, call the internal function, release the resources, and return the value, which kind of complicates things. Using a critical section like here allows you to recursively lock it, and this is really useful. If I recall correctly, Qt also has such a recursive mechanism, and of course if we write our own we could also implement it. That's obvious. But what we also can do, by the way, is we can use a synchronization mechanism provided by the standard template library, where you also have the option to choose if you want a simple locking mechanism, which will break if you try to lock it twice, or one which is recursively lockable. So this will be a thing that we do next. So as you see, with regard to locking threads for access synchronization, we really have a lot of possibilities. One which we will be not looking into is Qt, since it requires us to install the whole Qt framework, and Qt is something which we will be doing in the next lecture. Not next lecture, next part of the lecture, I mean. So next semester we'll be looking into the Qt framework and creating applications with a UI and stuff like that. So it will not be that low level anymore. But here, of course, we want the what was it? Mutex? Yeah, I think so. Okay, this we can comment out as well. Oops. And one more thing which is important to be mentioned with regard to all those synchronization mechanisms. Here, when we only are synchronizing access to one element, it is kind of simple, but as soon as you would have like multiple variables, and for example you would want to guard each of them with a different mutex. For example, as an optimization, that usually you have functions which only access one of them, and only sometimes you have a function which needs to access two of them at the same time. There you can run into deadlock scenarios even if you don't forget to release anything, because for example, you have a function which locks mutex 1 and 2, and then you have a function which only locks mutex 2, and then you have a function which only locks mutex 1. And imagine the scenario: your threads are running, your threads are doing something. Well, a function that locks both of them is entered. A function first that locks 2 gets entered, mutex 2 is locked. Then, and it does something. Let's say the function needs a longer time. And then you another thread calls a function that locks mutex 1 and 2. Since the other one which locks 2 is already entered, your function here can only lock mutex 1, but it fails to lock mutex 2. So you are in like a half-locked state. And then any thread that would want to do something with which requires lock to mutex 1 will also have to wait. And only if the function that locks 2 unlocks, your function which locks both of them can lock 2, do its thing, and then unlock both. If now the function that locks 2 would call a function that locks 1, which normally might be fine because you expect only one of them to be locked. If this happens, but your other function that locks both has one lock on one, then you are in a situation from which there is no escape, because your function that has to release 2 in order for your other function to be able to do its thing and release 1 is now waiting forever on 1 to be released, and 1 will never be released until 2 gets released, which will until as you notice, it's confusing. Even if I try to explain it, it's really easy to confuse oneself. So a good approach is to not try to have like multiple logs for multiple things, unless you really know that it's impossible. Let's say highly unlikely is not good enough for us. We want impossible. That you will end up in a situation where for some reason you will have such a scenario where something holds one lock, waits on another, and might never get it. So in such situations that can be arbitrated. You could make it like locks with timeouts. Like you try to lock both with a very short timeout, and if you fail, then you just wait and then you try again. So there are ways around it, but you should really try to avoid a situation in your code when you hold one lock and wait for another lock, because this is kind of asking for trouble. This might not always be completely avoidable, but often it is, and you should avoid it, even if it means that you need to like make temporary copies of things, make your code more unelegant, duplicate code in some places. This is all fine as long as you avoid waiting for a lock while locked, because as said, you might find yourself in a situation like with the other examples where it gets really hard to trace down what actually happens. And in fact, strangely enough, Visual Studio as is, at least in the simple versions, I think the Community Edition, does not really give you good tools to debug that. I think in the Enterprise and Professional Editions you have some automated tools that kind of try to help you to find such problems. But it's still kind of, in my experience, the most effective thing is just to take a good task manager like Task Explorer, or System Informer is also very good, but it has a completely different interface and I don't like it. I prefer this one. And then you just inspect the threads, because you kind of will see where those logs are waiting. So you will see that one thread is waiting for something and another thread is waiting for something, and then you can look up in your code what they are waiting for, and from this deduce what already is logged, and then you will find probably the culprit. And then of course fixing it is another story that also might be difficult. But anyhow, we wanted the mutex, so we have it here. Since it's a modern C++ construct, it has a constructor, it has a destructor, it does everything for you. So you don't need to create it or enter it or anything with special functions like we needed for those more low-level Windows functions here. We just have it and we just use it. So mutex params mutex.log mutex.unlog, and voila, as simple as that, and it will work. You might, if you know, so usually when you have little contention, most of those mechanisms, obviously except this one, will be quite good. When you have a lot of contention, they might not. So it might be if you see performance issues related to synchronization on your system, basically that you see, for example, in some profilers, that it's spending a lot of time waiting for something, or when you just run a synthetic benchmark, it might be good to try some of those mechanisms, because, for example, the critical section is much faster than the STL mutex. So if you have to enter and also lock it and unlock it millions of times per second, somewhere in your code, it is good to make such a comparisons and then pick the mechanism that is most suitable for your use case and gives you the best performance. Obviously, if you write platform independent code, you would not want to use neither of those, because you cannot use it on Linux or Mac. You would either use Qt's implementation when you use Qt, or you would use the STL implementation, which is present in any modern C++ compiler. So this is something to keep in mind. And one thing we have not mentioned yet is what happens if you throw an exception. Well, nothing good. Let's say it like this. Let's say this function here would fail to allocate memory because it needs to grow the vector. Then it will throw an exception, and then the thread will exit. It will not execute the mutex unlock. That's bad, because then the other thread will lock forever and the application is broken. So can we avoid that? Obviously we could put like a try and catch around it, would work, but then whenever you are using any sort of mutex, using also having to create a try and catch, and then maybe a try and catch all and so on, that's not elegant. But as we might remember, if we have objects created on the stack and we throw an exception, then the destructors for these objects will be called. The stack will be unwound and the destructors will be invoked, meaning that if we wrap our logs in some sort of object which will automatically unlock once it goes out of scope, then we can avoid such issues. And we could of course now write an object like this, but why bother? STL has this covered for us. It has a std unique log, oops, small s, unique log, I think it takes a reference on param. Are we missing a header? Oh, yeah, missing something. Okay, then it doesn't want a unique lock explicit for mutex reference. It should be fine. Why is it liking that? Params mutex. I don't think I have a typo. We found that thingy. I know why. We don't have the right C++ version enabled. So this thing is a template, and the unique lock can work on more than one mutex type. And since we don't have C17 enabled, it wants to know what it will get. In C17, such definitions will automatically deduce the right template argument from the thing that was passed to it. But the default, even in Visual Studio 2022, the default when creating a new project is C13, not C17. And of course, the standards go already up to C20, and C23 is already in preview. So actually, let's be modern. Let's just go here with C17, and then we don't need this redundant thingy. And the thing will lock it, and as soon as it goes out of scope, so we don't need any unlock or anything. Now, if we want, we can unlock it, and then later we can relock it, release, or just lock it. Unlock, lock, yeah, lock and unlock. In Qt is, I think, unlock and relock, and this is just lock and unlock. So it kind of proxies those calls on the mutex, but internally it keeps track whether it's locked or unlocked, and when the destructor is invoked, it will then automatically do the unlock for us. So here we can put this here as well. And now if an exception would to happen, which we hope it won't, but it could, it will be fine, because when it happens, then the destructor for this thing will be called, and this mutex will be released. And of course, we could implement this for our own, for critical sections, or for just a mutex, or for a spin lock. But as said, why bother? These mechanisms are given to us by STD. And there are more mutex types, which I just want to mention. Recursive mutex. That's the one that behaves like the critical section, and we have what was it? What was the name for that? Shared mutex, I think. No. I do not recall. I think it was something like shared, or there is a mutex type that allows you to specify whether you are performing a read or a write access. It is shared mutex. Why doesn't it? Did I have a typo? Okay, maybe it has an own header. That can be. So the more exotic things are in own headers. Yeah, shared mutex is in an own header. And the idea with this mutex is that you can lock it for reading or for writing. And the idea is that locking for reading, you have lock and lock shared. So lock is just lock exclusive, meaning you can write to it, you are the only owner. Or you can lock shared, meaning an arbitrary amount of threads can obtain a shared lock at the same time. So 3, 4, 10, 100 threads can all own a shared lock on this mutex, and if another one comes, it will also get it. But if a thread comes along and says, I just want an exclusive lock, then that will wait until all the shared locks are released, and non-new shared locks will be issued. And then you get your exclusive lock, you can modify the structure, unlock it, and then other things can again access it with the shared lock, and then they will be able again to get parallel access. And for reading, this is safe. So if you implement your I mean, if you would implement your class such that it has a count of read accesses, then that's of course not good. But in most cases, things will be implemented such that you can have multiple read accesses at the same time. They will not influence each other. Only writing will break things, so thus only writing needs to be exclusively guarded. It's kind of the same way like it works with the cache lines, as I mentioned earlier with this in the CPU. You can have all the cores, each of them owning a copy of the same cache line, as long as they are all just reading from it. But as soon as one wants to write to it, all the other CPUs, in this case, in the CPU case, the cache line is forcefully evicted, while here you don't have the option to like forcefully unlock another thread. That would not be a good idea. That would make the other thread would not be aware of that, and then it would start crashing and things like that. So that's not good. But it's from the idea, it's conceptually similar, that you can just have either one exclusive write access or multiple mutually non-exclusive read accesses. One thing that STL does not give you is a shared recursive mutex, as far as I know. Yeah, it does not. Which is kind of annoying because that would be really nice. And Qt in fact gives you such a thing. In Qt you can have a so in the Qt it's not called a shared mutex, it's called a read-write lock, because it's for reading and writing, it's more descriptive. But this read-write lock can be recursive, so that is quite nice. Here with the STL you are a bit more restricted. And of course, if you want to lock for read access, you would not use unique lock, but you would use shared lock. Yeah, so far to this. Anything else? Yeah, just on the Windows side of things, if you want to kill a thread, you can just terminate thread, which takes the handler, and you can even specify an exit code for the thread to then present. But this is not something you should do, because that really kills the thread dead in its tracks. Nothing will be cleaned up, the stack will not be unwound, all the resources, memory, all the logs that the thread might hold at the moment will just stay there indefinitely. So killing threads really is not something you should be doing. You can, so where it is acceptable, for example, where I do it often is when you shut down your application and you know you have a few threads that do things, then you can do two things. You can either wait for them indefinitely, or if you know that what those threads are doing is no longer relevant once a shutdown command was issued, what I do is I wait 10 seconds, and if the threads don't close gracefully within those 10 seconds, I kill them. Because the next thing the application will do, or the, maybe not next, but the thing further down the line of the execution soon will be to terminate the whole application, meaning all the dangling resources will then be cleaned up by the operating system anyways. So at this point we just don't care, and it's better than have an application which when you try to close it might deadlock for some reason. So that's one place where I find it reasonable to do it like this. Okay, and since we are already running out of time, and we only have 2 more lectures, so next week is, as far as I know, a holiday. Then we have 2 lectures, then there is a holiday, and then the semester is already over. So you need a final project, and as it's customary with part 1 of the course, the assignment is always the same. It is to create a own class of which will be able to represent any sort of data type. Such a class is called a variant. It's called my variant, and so I will just paste the assignment text that I always use. So the final project is to create a C variant class. The class has to be able to represent integers 8, 16, 32 and 64-bit, signed and unsigned, floats and doubles, strings and white strings, And now the complicated thing. It should also be able to represent arrays of variants and maps of variants. This is something that the Qt variant, for example, can do. But, for example, many simpler variant classes, like, for example, the variant that STL gives you, cannot. So, the variants, and the last thing, of course, that we want to be able to represent is just a not closer specified array of bytes, so that you have like some sort of blob type that we can feed with anything. The variant must have a constructor for all the relevant types, so that you can create something is equals this thingy. It must offer functions which allow you to explicitly cast the variant to a certain type, like cast to string, cast to int, etc. The variant should support mathematical operations whenever possible, in the sense whenever reasonable. It should be rather when. So that if you have two variants which are integers, you can add them together and you will get the sum. If you have two variants which are strings, if you add them together, you concatenate them, stuff like that. So you just need to implement the plus minus operators. As we have seen, this can be done. We had this example somewhere with this Mac. Was it in templates? We had this object that represented a Mac. One of the projects which we have done. It wasn't here. We close that. In operators, we have array. Here it was, MAC address in the operators CPP. So here you see, for example, how to do plus and plus equals and so on, and you can use this for all the operators. So what we want is such things on our variant as well. And the variant should use exceptions. So if someone tries to do something that makes no sense, like divide a number by a string, and then it should throw an exception saying that the types are incompatible. And to simplify the assignment, you are allowed to use a STL containers like map and list and vector to create those two types. So you can hold data internally in those. You could also, if you want, use a STL string to hold string data, stuff like that. Obviously, ideally you would try to do it as low level as possible, but if you want to have a good access performance, you need to at least cache the keys. So this is a major help to you to do it like this. I said that the variant should be able to convert between types whenever it's possible. So for example, if you call to string on a number and it is a number, then it should use, for example, sprintf to format the number as a string and return a string. If you have a string which contains a number, not the word bananas, but if it would contain 1 is also fine, then it should be able to do the division. It should basically try if you are doing a mathematical operation, and it kind of might be reasonable, because for example, if you would try to divide a number by a map, that always fails outright. That makes no sense. If you try to divide anything by a byte array or a byte array by anything, that fails outright. But if you have integers, floats, or strings, so integers and floats must work. If you have strings, you have to check whether the string can be interpreted as a number, and if it can, then you can do it. I think we have seen the attoy or vtoy function sometime during the lecture, which does that. If not, you can always use scanS, which works like sprintf, just in reverse. So this should be easy enough, and there is a couple of optional assignments. So things that you can do, but you don't have to do them. If you do them, you get extra points which you can use to fill up for homework which you didn't manage to complete and stuff like that. You can create okay, this I have not shown you, so this unfortunately we cannot do. You can add support for array types. So currently, if you have an array of variants, then you have like an array of variants. So every single entry from this array, if you want to access it as string or rather as number, you need to cast from the variant to this number. So this adds operations. You could, however, implement support for types. So you have just a native C array of ints or doubles, and then if you try to access one of them by index, then it is much more performant. What you also could do is add the option to serialize the variant to some other representation. So whether to something like JSON, XML, or your own invented representation as a binary format, so that you can save it to a file and then load from a file. So as you know, more complex objects in C++ cannot be dumped and just copied, or dumped to a file and loaded from a file, because they contain memory addresses which, once reloaded from a file by a different process, would be invalid. So when writing things to a file, the process is called serialization and deserialization. And there, the idea is that you change the format such that it would, for example, only contain relative offsets for within the file itself, or stuff like that. How you do it is up to you. You can pick a format. Bencode would also be a good and simple candidate. And it's quite useful. So if you have variants, being able to serialize them is a very powerful thing, because as soon as you would have, for example, some network communication or inter-process communication between two processes, then you would find yourself in a situation where you would want to be able to send some complex data to some other process through a connection which just relies a byte stream. So this is very, very useful. Yeah, and that's pretty much it. The rest just explains the so let's maybe number them 2. But we can add a further assignment, a further optional assignment 3. Add iterator support, so that you can to variants containing of variants variants which are a container type. Oops, map list array. That would be quite useful. So you had the iterator assignment assigned during the last homework. I think I uploaded also a updated version of my array, which implements a simple iterator. So just when doing the homework with the iterator and when doing it here for the variant, you can look it up in the my array implementation, how a very basic iterator would operate. It implements the minimum amount of functions needed for it to work. Yeah, and this would be it. One more comment which I maybe should add here. Map, list. Actually, I should call it a vector, because it's not a list. Yeah, arrays of variants. My vector must implement the content by index and map case by key. is an ANSI string. Okay. Any other instructions I might want to add? Yeah, the variant should not be a template type. The variant should not be a template type. So it should not be like that you have templates which then get specialized, but the variant should really, as a standalone object, be able to handle all the types it is supposed to handle. You can use templates to implement some of the functions whenever appropriate, but the main thing should be a fixed variant type without which does not get specialized, because otherwise it will get too complicated. Okay, are there any questions to this assignment? Does it sound doable, or do you find it too complex? Okay, let's try it out. That's the spirit. So I will upload the projects from today to the Moodle, the assignment as well. I will just upload only the text into the task thingy. I will not upload the empty project because that's kind of pointless. And for the next 2 lectures, the things we will do, I think, so if you have questions to anything, you can think about them. You have 2 weeks to think about questions and ask them during the next lecture, especially if you would want some more input about these iterators here maybe, or any other mechanism. That would be the right opportunity to do so. Once we are done with all the questions that you might have, we will try some hacking around C++. So we will create a mechanism that will allow us from just C to interact with C++ objects, which will be quite funny. And in the last lecture, if we have enough time, we will try something rather fun, which might be function hooking. That is, if you would want to modify the behavior of a Windows API for an application just by loading some DLL into that application, which will override native Windows functions. This is not doable like global. You cannot override globally a Windows function for all the process in the system. But if you inject code into any process, this code can override parts of the copies of the system libraries that are valid for this process. So on Windows, like when you load a DLL, it's loaded somewhere into memory, and all the processes that try to use it get an access of the type copy on write, meaning they have the thing, they can read from it, and if they would try to change any of the pages of the DLL, then an exception is triggered. The page is copied to a page which then is exclusive to the process. In the process's memory layout, this page, the original page is swapped for the exclusive page, and then the operation is retried, and the application can overwrite it. So, for example, you can overwrite inside any process you get code execution parts of the NTDLL of the kernel 32 DLL, and for the current process, this will change this library's behavior in the way you want it, or rather in the way you wrote it. And if you wrote it correctly, then it will be the way you want it. If you did it wrong, then it will do something else. Okay, but I think this is a good point to finish. So you have an assignment. During the next two last lectures, there will be no more homework assignments. You will have enough to do with this variant project. I think it's not too complicated. So in the past, it always worked out well enough. It's just a bit labor intensive if you need to make everything for like all the different integer types. So for example, here it might be useful to try to use a template to not have to duplicate like 8 functions for integer sizes, and that times 2 for signed and unsigned. But this is up to you. You can also just by hand copy paste the function 8 times, change the types, and that will be also fine. Generally, if you find yourself rather what's the English expression for that? Unsicher. not very sturdy on your feet in C++, then I would strongly recommend to avoid trying to create an own template class or use templates creating own templates, because those create, as we have seen, bugs which are rather hard to fix, and it might not be easy. So it's better if you try to make this project just as normal C. You can of course call template functions, use the STL template classes, because so using templates is usually not so difficult if the template is well crafted. Creating your own templates is a different story. So this is just a hint for ease of implementation, and we'll see each other next month. Yeah, that's that. Stop